Hello and welcome to Office Hours. Actually, I think this is our 8th week. Yeah, and I put week 7 in the title. Let me fix that. It may not be morning, but I still have a cup of coffee. And I want to know, as always, do you have any questions? I have been buried under a pile of grading, which I will continue to work on unless any of you come by and happily interrupt me. I'd much rather talk about chemistry than grade chemistry. So be my liberation, be my escape from grading. Drop by, drop me a question. I'll keep my eye on the chat. If not, this will be a stream of watching me grade. Sarah, I totally can. Here, let me pull up the eLab 6 stuff, and I'll march right through it. It's totally fine that you're at work, because beauty of YouTube is it's always up in here. All right, here. Just give me a sec. Oh, weird. The post-lab calculation link is dead. Okay, here, give me 1 sec. Sorry, hang on. I am checking to see the link's dead, but I don't know if it's the lab report. Okay, there we go. Sorry. Copy link address. Let's fix this. Okay. Data analysis. Okay. So, I'm gonna bump this over here. Pull that there. All right, so this is a Chem 400 question. About ELAB 6. All right, and this is the data. Now, okay, so Sarah, you're asking about the calculations for questions 1 and 2 in the data analysis. Okay. All right, so this is data analysis. Actually, let me make this a little more compact. So ELAB 6 data analysis, and this is 1A. So they asked us, calculate the amount of heat evolved for the reaction, Cube reaction. All right, okay, so here, let me see. I'm going to need some data. So I'm going to look at the data assignments and then then once I have a data assignment, then I will be able to do this problem. So all right, so here, let me just generate for myself a data set. Data. So this is for reaction 1. There we are. All right, so I have my concentration of HCl is 3 molar. My density of HCl is 1.5, 1.05 grams per milliliter. My concentration of sodium hydroxide is also 3 molar. My density of sodium hydroxide is 1.11 grams per mil. My specific heat of the solution is 3.94. This is grams, sorry, no. This is joules per gram degree C. And then my heat capacity of the calorimeter is 15 joules per degree C. this over down here, and then I have some additional data. All right, so I have my volume of HCl. Is 49.96 milliliters. My temperature of HCl, 21.8 degrees Celsius. I've got my volume of NaOH is 49.85 milliliters. The temperature of sodium hydroxide is 21.9 degrees Celsius. And then the max temperature is 41.9 degrees Celsius. Okay. All right. So this is so here's my data set. Now that I have it, let's start talking about the problem. So part A is calculate the heat evolved in the reaction. All right, and conceptually, here's what's going on. We have two solutions, right? We have HCl, and we have NaOH. This is at some initial temperature. This is at some initial temperature. And what we're going to be doing is we're going to be pouring both of these solutions into a beaker, filling it up, and these two are going to react. The reaction is going to release a ton of heat into the surroundings. And the thing is, we're doing this inside a calorimeter. So the temperature of the water is going to go up, of the solution, but also the temperature of the calorimeter itself is going to absorb energy. All right, so the key conceptual thing to note is that the heat, so the heat of the reaction is absorbed by the solution and the calorimeter. All right. The calorimeter, i.e. the container. All right. So the heat lost by the reaction is absorbed by the solution and by the calorimeter. So the heat absorbed by the calorimeter plus the heat absorbed by the solution is the same heat that is absorbed, or that is released, excuse me, by the reaction. Because the reaction is losing energy, energy has a negative sign because the solution and the calorimeter are gaining energy. They have a positive sign, so we need to multiply one side of this reaction by -1. And this is the equation that we're going to use to calculate the heat released by this reaction. Right, our final temperature is the temperature once it stops rising. All right, the max temperature that you find on your data sheet. All right, so this is the key equation that we're going to use. You'll notice that there are two components to this thing. All right, so we've got our Q of reaction is equal to -1 times the Q of our solution plus the Q of our calorimeter. And Q, remember, is heat absorbed or released. Now, Q for our solution, actually, I'm going to write it over here. This is where we use Q equals MCAT. It's equal to the mass of the solution times the specific heat capacity of the solution times the change in temperature, right? Whereas the Q for the calorimeter is just equal to the specific heat capacity of the calorimeter, not the specific, the heat capacity of the calorimeter times the change in temperature. All right, so these are the two things we need to find. Before we begin, I want to say a quick note about the delta T, all right, because this is going to be the same for both. Now you'll notice, well, so we know that a change in temperature is equal to the final temperature minus the initial temperature. All right, and the final temperature right here. This is the max temperature given to us in our data assignment. But T1, you'll notice there's two different T1s. There's the temperature of the sodium chloride solution, and there's the temperature of the HCl. So which one do you use? The answer is you use the average. Use the average of T1 HCl and T1 NaOH. All right, so that is the temperature that we're going to use for our initial temperature for both these calculations. And it's not a bad place to start. Let's go ahead and knock that one out. So let's take a look at our data. Whoa, let me blank that out real quick. Just going to do that because it's easier for me. Now I have it as a reference. I won't have to keep popping back onto that screen. All right, so let's calculate our delta T. First, let's get our T1, which is an average of hang on. Oh, sorry, microphone. So it's going to be an average of our HCl temp plus our NaOH temp. So our HCl temp is 21.8 degrees Celsius. Our sodium hydroxide temperature is 21.9 degrees Celsius. We add these together and divide by 2. Oops. 21.8 plus 21.9 divided by 2 is 21.85 degrees Celsius. Now we are going to be limited to 3 significant figures, so I'm going to put lines there to remind me. I'm going to wait to round till the end, but I'm putting those lines there to help me remember. So now we can calculate our change in temperature. Because our maximum temperature was 41.9 degrees Celsius, minus our initial temperature, 21.85 degrees Celsius. And now we take the difference, 41.9 minus 21.85. My calculator is telling me that my answer is 20.05 degrees C. Sig figs wise, for both of these numbers actually, our last significant digit is in the first decimal place, so this number also has its last significant digit in the first decimal place. Gonna wait to round to the end, but this number has 3 sig figs. Just like our initial temperature and our final temperature for that matter. So there's our delta T. At this moment in time, we can calculate the amount of heat absorbed by the calorimeter, because it's just equal to the heat capacity of the calorimeter times the delta T. We just calculated delta T, and we've been given the value for our heat capacity, which was, I believe, 15 joules per degree C. Let me just double check. Yep. 15 joules per degree Celsius is our calorimeter's heat capacity, and our change in temperature is 20.05 degrees Celsius. Remembering that this number only has 3 sig figs. All right, so we're good to crunch numbers again. 20.05 times 15 gives us a value of 300.75 just joules, actually. If you look at your units, degrees Celsius cancels degrees Celsius, so our units are joules. Sig figs wise, our delta T has 3 sig figs. Our heat capacity has 2, so this number only has 2. And it's not our final answer, so I'm not rounding yet, but I'm putting these lines there to remind myself that the value for heat absorbed by the calorimeter has 2 significant digits. All right, so that's our heat capacity. Sorry, no, that's our heat absorbed by the calorimeter. Now we need to calculate the heat absorbed by the solution. All right, so this is equal to the mass of the solution times the heat capacity of the solution times the change in temperature. Now, we know our change in temperature, right? We calculated that. We're given heat capacity of the solution. We are not given, however, we're not given the mass of the solution. All right, this is piece we have to figure out. All right, now let's look at what we're given. Okay. The mass of the solution, once we mix our sodium chloride and sodium hydroxide together, is going to be the sum of those two masses, right? It's going to be the mass of HCl plus the mass of sodium hydroxide solution added together. Now, we also haven't been given the mass of HCl or sodium hydroxide. However, for each one, we've been given the density and the volume. All right? We've been given density and milliliters of each. Now, density is equal to grams over milliliters. So if you solve the equation for density, you'll see that the mass is equal to the density times the volume in milliliters. So we can find the mass of HCl and the mass of sodium chloride by multiplying the density and the volume of each. So this equation becomes the mass of our solution equals the density of HCl times the volume of HCl, and the mass of sodium chloride becomes the density of sodium hydroxide times the volume of sodium hydroxide. And we've been given both of these. So the mass of the solution is equal to the density of HCl, which we have right here. It's 1.05 grams. Excuse me. Per milliliter. And the volume of HCl was 49.96 milliliters, plus the density of sodium hydroxide, which is, for my data set, 1.11 milliliters, times the volume, which is 49.85 milliliters. All right. So we've got some multiplication to take care of. 1.05 times 49.96 is 52.458, and you'll notice my units are grams because milliliters cancel milliliters both times. Sig figs wise, I can only keep 1, 2, 3. So I'm going to remind myself there, that's the mass of the HCl plus my mass of sodium hydroxide. 1.11 times 49.85 is 55.3335 grams. Again, also we're limited to 3 sig figs here. Now we add these two together. 52.458 gives us, for a massive solution, 107.7915 grams. And notice here, okay, we're not counting sig figs because we just added. You're looking at the last significant digit in the number. Our last significant digit must be in the first decimal place, so this value actually has 4 sig figs. All right, now we have our massive solution. We can actually calculate the heat absorbed by our solution now. So this is equal to 107.7915 grams. Again, remembering that we have 4 sig figs in this value. Our heat capacity, specific heat capacity of our solution was given to us. It's 3.94 joules per gram degrees Celsius, times our change in temperature, which is 20.05 degrees Celsius, and you'll recall that this number only has 3 sig figs. So now we can multiply all of these together. We have our mass times our specific heat capacity times our change in temperature, which gives us the heat absorbed by our solution is equal to, not 5, 8,515.20513. Units wise, grams cancel grams, degrees Celsius cancel degrees Celsius, leaving us with joules. Sig figs wise, we're limited to 3 by the specific heat capacity and by our temperature. Again, we're not rounding yet. We're saving that for the last step of the problem, but we are putting these lines to remind ourselves that we have 3 sig figs. All right, now that we know the heat capacity for our solution, the heat absorbed by our solution, and we know the heat absorbed by the calorimeter, we can add them together to find the heat released by the reaction. Remember, Q of the reaction is equal to -1 times Q of the solution plus Q of the calorimeter. Now, our Q of solution, or actually, I'm just going to write this down here. Q of our solution is 8,515.20513 joules. And again, we have 3 sig figs in this number, plus the Q of our calorimeter, which was 300.75 joules. We also have 3 sig figs in this number. Let me just make sure I got that down right. Yeah, okay. Wait, no, hang on. Yeah. Oh, 2 sig figs in that number. I'm glad I checked. All right, so I wrote that down wrong. This number only has 2 significant digits. Okay. That's why we always double check. So Q for our reaction equals the sum of these two, which is negative 8,815.95513. Looking at your significant figures, we have to look at the last significant digit in each number, which they both have their last significant digit in the tens place. So we must round our answer to the tens place because this is the end, so this is where we round. 5 is going to round up. So this will give us the heat released by this reaction is equal to negative 8,820 joules. All right. So that is the heat. That's part 1A. As you can see, we've got 10 minutes left. I'm going to be able to finish 1B, but once I walk you through these steps, it's the same thing for the next part of the data analysis. If you want to see those worked out, I can totally do them tomorrow in office hours, so just let me know. But let's go ahead and finish this one out. So that's part A. We've got our energy released by our reaction. Let's look at part B. So 1B. Calculate the value of the enthalpy change in terms of kilojoules per mole. Okay, so they want us to calculate the change in enthalpy for the reaction. Now, change in enthalpy, the way you calculate the change in enthalpy, it is the energy, change in energy for your reaction. Here we're just going to do, it's the Q of the reaction we just calculated, divided by this right here. This is moles of limiting reactant. All right, so we calculated our Q of reaction in 1A, right? This was negative 8,820 joules. They wanted in kilojoules. Which is negative 8.82 kilojoules, so that's our numerator. Now our denominator, we need to determine the moles of limiting reactant, all right? We've got two reactants in this problem. We have sodium hydroxide and hydrochloric acid. Now, to calculate a limiting reactant, we need to actually look at our chemical equation. These two will neutralize each other, right? HCl, sodium hydroxide, to produce water and sodium chloride. So we need to do a limiting reactant calculation. Now we're told that we start with 3 molar HCl, which is moles of HCl per liter. And the volume of HCl that we're given was 49.96 milliliters. So we got to convert that to liters, excuse me, first. All right, so that we multiply these together to cancel our volumes. Now we have moles of HCl. Next, you can pick either product, water, or sodium hydroxide. Does not matter which one. We just need to know which reactant is limiting, so which one produces less of the product. So we're going to go 1 mole of HCl over, 1 mole of H2O over 1 mole of HCl. If you pick sodium hydroxide, the answer would come out the same. Moles of HCl cancel. So this would give us 3 times 0.04996. So If HCl is our limiting reactant, we would produce 0.14988 moles of water. And sig figs wise, this is 1 sig fig, so our answer would only be able to have 1 sig fig. Let's repeat this calculation for sodium hydroxide, and that will show us which is our limiting reactant. We need to multiply our molarity of sodium hydroxide by our volume in liters. So our volume of sodium hydroxide was 49.85, I think. 86. No, 85, sorry. 85. 49.85 liters. So liters cancel. Next, we're going to convert our moles of sodium hydroxide to moles of water. Moles of sodium hydroxide cancel. And now we can calculate how many moles of water would be produced if sodium hydroxide is the limiting reactant. 3 times 0.04985. So this would be, 0.14955. Sig figs wise, it's the same. We're limited to 1. Now, this value is smaller. And because this is a smaller quantity of moles, that means for my data set, sodium hydroxide is the limiting reagent. All right, now that we know that sodium hydroxide is the limiting reagent, we can calculate how many moles of sodium hydroxide were consumed in this reaction. We can do so by multiplying our molarity of sodium hydroxide by our volume in liters. All right, so this gives us 0.14955 moles of sodium hydroxide. We can only keep 1 sig fig because of our molarity, but we're still going to use the whole number to calculate our change in enthalpy for the reaction, which is Q of the reaction over moles of limiting reagent. So our Q of the reaction is negative 8,820, 8.82 kilojoules over moles, which is 0.14955. There's only 1 sig fig down there. So my calculator is telling me that the answer is 58.9769308. But because I can only keep 1 sig fig, that 8's going to round up. And we get a delta H of reaction is negative 60 kilojoules per mole. All right. And so we're out of time for this office hour. However, the data analysis for step number 2 is pretty much the same. The reason why I say pretty much, the only difference is one of your reactants in step number 2 is a solid. So instead of having molarity and volume for both, one, I believe you're just given a mass. Again, if you want to see me work that out, I totally can in future office hours, but I got to run for this one. Sarah, thanks for asking a great question and helping me procrastinate my grading, which now I have to get back to. But I'll be back tomorrow, 8 a.m. Office hours. Hopefully, I'll see some of you then later.